Hey, what's up guys? In this video we're going to be talking about the Fibonacci sequence and how you can use it to understand recursion in code. You'll find that more often than not you'll come across the Fibonacci example when learning how to write recursive code. In this video I'm going to attempt to break down and explain things to you in an easily and comprehensible manner, starting with the Fibonacci sequence. From a programming perspective, we can think of the Fibonacci sequence as a series of numbers represented by an array. Each index of the array we will prefix with an F for Fibonacci. For example, index 0 of the array we will refer to as F0. So this means that we can refer to the nth index of the Fibonacci sequence as Fn, where F represents Fibonacci and n represents the nth index of our Fibonacci array, resulting in something that looks like this. Next, we will fill in the first 4 Fibonacci numbers. Now don't panic just yet. We will go over where these numbers come from soon. For now, it is only important to understand that we can now conclude that F4, or the 4th Fibonacci number, is 3, the 3rd 2, and so on and so forth. So where did we get these numbers? The answer is actually quite simple. F0 and F1 will always equal 0 and 1 respectively. So nothing needs to be done to get the first 2 Fibonacci numbers. You can consider them constant. Getting the rest of the Fibonacci numbers is also quite simple. Each Fibonacci number is the result of adding the 2 previous Fibonacci numbers together. So this means that to get F2, we just need to add both F0 and F1 together. And to get F3, we just need to add F1 and F2 together, and so on and so forth. Now here's where things begin to get a little bit tricky. The mathematical way to describe what was discussed in the previous slide looks something like this. This is what we would call a recursive formula for the Fibonacci sequence. It's a recursive formula because it's a formula that defines each term or Fibonacci number of the sequence based on previous terms. For example, to determine the value for F2, we must know the values for F0 and F1. Just like in our last example when we found that Fib2 could be determined by adding the values for Fib0 and Fib1 and so on and so forth, this formula is just a mathematical way of describing the very same thing. Let's once again write out our Fibonacci sequence and see how this formula is actually applied. Let's say that we want to figure out the value for Fib6, or in other words, which Fibonacci number is at the 6th index of our Fibonacci sequence, which we are visualizing as an array. Assuming that we only know Fib0 and Fib1, which always equal 0 and 1 respectively, we will need to figure out every index up to Fib6 to determine the value for F6. And as mentioned before, the fact that we need these previous values to determine the value of Fib6 is precisely what makes this formula recursive. Let's take this a bit further by applying the formula for Fib6. So Fib6 is equal to Fib6 minus 1 plus Fib6 minus 2. So Fib6 is equal to Fib5 plus Fib4. But we have a problem here. We do not yet have values for Fib5 and Fib4. So we must start by finding Fib2 and moving up from there. To find Fib2, we'll take advantage of our known constants for Fib0 and Fib1 and progressively move up from there. It's important to remember that we must always first start by stating the initial terms, which are F0 and F1, because without these as our base, we cannot use this formula to determine the rest of the values in the Fibonacci sequence. Now this, ladies and gentlemen, is the formula that we're going to use to implement Fibonacci programmatically, so let's take a look at how it works. To start, let's ignore all of the surrounding code and focus on the actual return value. The return value should look familiar as it is the mathematical formula that we discussed in the previous slides, just in the form of code. As you can see, whenever this function is called, it will recursively call itself. Let's try to visualize this. Now let's imagine that every time the function fib calls itself, we go deeper into a tree structure. For every one call to the fib function, we must call the fib function 2 more times and then add them together. Now you will notice that some of these nodes, like this one for example, is not expanding into more nodes like the others. This is because after doing the math in the parentheses, the result is either fib1 or fib0, and if you remember, both fib1 and fib0 will always equal 1 and 0 respectively. This will be the case for any node which the result is equal to 0 or 1. Now that we have gone as deep as we can now make our way back up the tree. So starting from the bottom here, we see that fib2 minus 1 is equal to fib1, which is always 1, and fib2 minus 2 is equal to fib0, which is always 0. When we add these together, we get the answer for fib3 minus 1, or fib2, which we can see is 1 because it is equal to the sum of the two nodes below it. And that can be added to fib3 minus 2, or fib1, which again is always 1, which tells us that fib4 minus 1, or fib3, is 2. We can do this until we have the answer for fib5 at the top of the tree. And finally, we see that the fifth Fibonacci number, or fib5, is 5. And now we can go back to the rest of the code, where we can see that all it does is check to see if the number passed in is 1 or 0. If it is, it returns 1 or 0 respectively. This is because, as mentioned throughout this video, fib0 is always 0, and fib1 is always 1. And that is Fibonacci in recursion.